Okay, I've got a piece of shelf standard is what this is. It doesn't matter too much what it is. Let's pretend it's a solid piece of metal, or at least doesn't have holes in it. This thing has holes in it, okay? Let's assume it's a uniform piece of metal with this kind of cross section. Again, not particularly important to the idea. I've got a 1.5 volt battery here, and I've got a couple of leads attached to the ends of the shelf standard, and I connect the battery. Now, presumably, I've got a current flowing through here. The battery's in here. Thing we want to understand is this thing produces 1.5 volts. So this end is going to be a positive 1.5 volts if this end's at 0. At least the potential difference between this end and this end. The electric potential goes up by 1.5 volts between here and here. Okay? Now, you don't know what that means. So I'm going to make some definition. I mean, you might know what it means, but you wouldn't know because what was done here is we haven't done it yet. Okay, so we have a potential difference. This is 3 centimeters long. This end is at plus 1.5 volts, which I'll just abbreviate like 1.5 V. Actually, I don't want to do that. I want to say what one end is and what the other end is. If we go from this end to this end, potential change is plus 1.5 volts. And the camera's out of focus. Should have put it a little bit better. Okay. Still doesn't want to behave. There we go. Just throw that away for a minute. Okay. So let's say we got a charge here of 4 microcoulombs. And over here, we have a test charge. At a distance of, let's say, 50 centimeters. Now this has nothing to do with this. In other words, 50 centimeters here has nothing to do with 30 centimeters here. It's just what we're going to say here. Okay, so if Q sub T equals plus 1 microcoulomb, find the force on QT and the work so see if you can outline what you would do Figure that out. Okay. So to do that, cover meeting, good answer. You got the force, or you got the distance. Okay, so we'll just say delta x. We'll just propose an x axis. Doesn't matter. We can arbitrarily do that. Okay. Now, of course, you better say it's the average force times delta x, because as we move from 50 centimeters to 49 centimeters, we know the electric repulsion is going to get greater. Okay, so work is the average force times delta x. F there's your strategy, okay? So at 50 centimeters, well, Q times QT is 4 times 10 to the negative 12 coulomb. Squared. So this is 4 times 10 to the negative 12 coulomb squared over we could write 50 centimeters. Of course, centimeters squared is not going to articulate with the meters squared there. So at some point we have to do conversions. So we might as well write this distance in meters. But it could be done either way, as long as you're careful about your units and write the units out like I keep telling you need to do. Okay. So that's a very simple calculation. Let's see, we're going to get 36 times 10 to the negative third over a fourth, which is going to be 144 times 10 to the negative second. I think that's 1.44. 10 to the negative 7. Now we'll pretend that's right. Right order of magnitude. You got a negative third here. Oh, well, I have the 9, 36, 144. Wait. 36 times 4 is 144. That's it. Okay. Okay, I think that's what 144 means, because this is almost 10 to the 10th, right? 10 to the 10th times 10 to the negative 12, so 10 to the negative second. And then 4 divided by 1/4 is 16. It's 16 times 10 to the negative 7, which would be 1.6. It's really only 90% of that, so that's right. Okay, so got that force. Now we've got to be a little bit careful. The force that's exerted on this thing is in this direction. So the force that we have to exert is got to be in this direction, right? So the work done, I often use a delta for that, but I just use that. Okay, the work done is done. But 144 newtons times 1 centimeter. If we assume that the force doesn't change significantly between here and there. So that's 1.44 times 10 to the negative third joule. That's assuming the force doesn't change much between 50 and 49 centimeters. That's going to increase by about 2%. So you might add 1% to this and get a pretty good approximation. But if you want to get it exactly, you just have to do a simple interval. I have to integrate this expression between the 2 points. That's easy. Okay. Next question. I have to think through how you set up that integral, why you set it up the way you do, and why you end up integrating what you do integrate. Okay, well, anyhow, assuming the force doesn't change much, there it is, okay? Now, that's on a 1 microcoulomb charge, right? Okay. Well, if QT test charge is 0.001 coulombs, how much work is done? Should be able to answer that almost instantly. So don't write for a minute, just think and see if you can answer the question. Okay, so I mean, you immediately see that's 10 to the negative third coulombs. Micro means 10 to the negative 6. Nano means 10 to the negative 12. Okay. So anyhow, there you go. Okay. I say nano is 10 to the negative 12. That's kind of echoing in my head. It's 10 to the negative 9. Okay. Anyhow, there we got it. So how much work is that? Well, we got 10 to the third times as much charge, right? So your force, which is proportional to Q2, right? So the work is 10 to the third times straight. Work equals 1.44. Assuming that I did those calculations correctly, okay? So my question then is, good question. How much work do we have per coulomb of test charge in the first case? Okay, well, you see this. You get this much work when you have this many coulombs. Well, there was 1 microcoulomb, okay? So it's going to be the work done by the number of coulombs, which is, in this case, 1,444 joules per coulomb. Okay. Now, of course, we could have reasoned it out here. you've got a different number of coulombs. What's going to happen if you do that? What are you going to get?
75 volts.
What?
Is it 0.75 volts?
What if you went 10 centimeters?
And so means a third to be half a volt.
So your potential goes up uniformly because your electric field is uniform. Okay? Now we'll make that connection. Oops, that wasn't being recorded. I don't know what happened. Okay, well, the post is, and I hope we pick this up. You have a 1.5 volt change of potential. I asked, what would the change of potential be if we went halfway? Immediately got the answer. Well, half of that 1.5 volts seems reasonable, seems logical. Haven't proved it, but yes, that's right. If we went 10 centimeters, got an immediate answer. Well, half a volt, because it's a third of the distance, and a third of 1.5 volts is half a volt. Okay. Now, I say 30 centimeter uniform conductor entails a uniform electric field. Okay, if your potential is created by some source between this point and this point, the electric field is going to be uniform. So you're going to have electric field in that direction. Question then is, what's the change in potential per meter? We'll come back to electric field in a minute. But okay, come back to our original question. What's the change of potential per meter? Okay, so let me use P ambiguously for the unit volts and for potential. Okay, could use pi. I'm going to use V because it's a pretty standard notation of circuits. Okay. I'm not sure you gave me units on that. But it's 5 volts per meter, right? Okay. Now, what's a volt? Yep, yep. Okay. So, yeah, okay, let's go back there. You were saying? Here's a question I want to pose. If you're electric, if this is electric field, that is, if E is 5 newtons per coulomb, which is the same as 5 volts per meter, okay, then how much work does the field do on a charge QT as you move from left end to the right end of this conductor? Okay, now you came up with a good answer. If you assume QT is 10 to the negative 6 coulomb, you said it's 1.5 times 10 to the negative 6 newtons. Okay. And then you multiply that by the 3 meters and all that stuff. And I think I said that wrong, but anyhow, you worked that out correctly. If you assume the QT is that specific number, of course, we use 2 different QTs, so there's no reason to assume that. But then I ask you to calculate, okay, that's okay, you got a good answer. So how many joules does that end up per coulomb? You end up with 1.5 times 10 to the negative 6 joules with a test charge of 10 to the negative 6 coulombs. It would give you 1.5 joules per coulomb, okay? Calculating it in symbols, just not putting any numbers in. Your F delta X is, well, here's your force, right? 5 newtons per coulomb, which would be your electric field times QT with a delta X of 0.3 meters, okay? And that comes out 1.5 newton meters per coulomb times QT, right? So your delta PE per unit of test charge it's kind of small there about space, but it's 1.5 newton meters per coulomb, which is joules per coulomb times QT divided by QT, which is just 1.5 joules per coulomb or 1.5 volts. In other words, assuming that this 5 newtons per coulomb is in fact your electric field, we figure out the force, the delta X, and the change in potential energy per unit charge, and we find out that it is 1.5 volts, which of course was our assumption, showing that this really is our electric field. It's another way of writing the electric field. Now, as I said earlier, just because the units come out, the units of electric field doesn't mean you've really got electric field. You got to go back to the definition of electric field and understand that. And I think you pretty much do. Make sure you review that soon so you don't lose it. It's going to be hopefully very helpful to you as you work through all the symbolic stuff, which I'm going to do anyway. Okay. So bottom line, electric field units and newtons per coulomb or joules per meter. The electric field tells you how many joules you have per meter, tells you how many newtons you have per coulomb. This gives you the force per unit of charge. This is the work per unit of distance. Done by that force. Okay. Okay, so let's do another one now. Let's say you have charge Q here. And you have a test charge here. At distance R. Imagine the QT started way far away and moved to this position. Question is, what was the change in its potential? Okay. Now, before we tackle that, you might want to look at just the idea of what happens. If you move now, charge BQ here, and a charge QT moves from distance R1 to distance R2 along the x-axis. So here's the path. The question then is going to be, so this is QT. Here. Okay. Yeah, I'm going to do it. We're going to want to partition this path into little increments. You saw before where we went from 50 to 49 centimeters, and we reasoned out by proportionality, or maybe I just mentioned it, that the force would increase by 2%. So just using the force of 50 centimeters gave us a pretty good approximation to the change in, well, to the work necessary, therefore to the change in electrostatic potential. We got 1,444 volts. Okay, went through that whole process. It should have been about ballpark 1% higher. Okay, so it might have been 1458. But to get it accurate, we had to do an interval. We didn't do the interval yet. Okay, if we partition this path, we take a typical instrument. You know what? I'm going to go ahead and use R. My axis. I'm going to call this an R axis. And then I'm just going to write this out. I'm not going to try to pull it out. I'm just going to do a few more things. I'm going to be a little more rigorous here. I'm going to say the work required is F delta Ri. And we'll just write it. I'll be a little careless. Okay. F delta Ri, where F equals negative symbol negative of K times big Q times 2T over Ri star squared times delta Ri. I'll call that delta WRI. And I'm writing the next expression before I have to think of this one. So there's my F sub I. Now what I wrote a minute ago when I think ahead. Next we have this. Well, this equals a bunch of stuff. We write out the sum and all that stuff. We just need to know how to write that out. We've done it so many times. You ought to be able to do it in your sleep. But it's a stretch to get from where you started to being able to just understand these intervals. You need to work on it. We need to really get this down. Okay. Anyhow, this is going to then be the integral from R1 to R2 of negative K big Q times QT over R squared dr. So and let me just pull out the constants there. I'm writing that about, okay, negative K big Q QT. And what's that leave? Leaves the integral of 1 over R squared dr R1 R2. In that integral, well, what is the integral from R1 to R2, 1 over R squared dr? Go ahead and look that up. Should just take a second. I'll write this out carefully, but you got it. And you see what the rule is. It's straightforward. So I'm going to say, okay, well, it's a negative Q QT times negative 1 over R evaluated from R1 to R2. Right? So you know that. That's kind of it. And this is then going to be, well, it'll be negative 1 over R2 plus 1 over R1 changing the signs, doing it 1 over R2 minus 1 over R1. Signs aren't agreeing. R1 to R2, negative, because it is. Got 2 negatives here. Okay, well, and as I said, this is right. Okay, so there it is. Okay, that's we're doing something wrong. Okay, now, noticing that in this picture, no, it isn't right. R1's out there, R2's here, it's integrating from R1 to R2. The integral has come out negative. The negative on that integral. Okay, I gotta stop a minute. Okay, must be sleep deprivation or something. Right. There's your total work, so you're changing potential energy. Is this. Okay, the potential is which is just K times big Q times 1 over R1 minus 1 over R2. Which is just the change in negative K times big Q over R. I'm not being very careful about my terminology. This is a total work. This is not the total work done by the conservative force. This is equal and opposite to the work done by the conservative force. So I really should have started this out with the secure definition, which I usually would do. And I just kind of did that and lost track of where I was. But this is equal and opposite to the work done by the conservative force. And I'm just going to say by magic, you got to look at the books derivation. It's the change in the quantity KQ over R. Now, the big deal about this is that this work is path independent. Okay? So it doesn't matter how I get from here to here. If I spiral in, loop around here, take a big excursion and end up here, doesn't matter how I get from here to here, the work is the same. Because the force is conservative. Take that back to the whole stuff we did in lower level calculus. And the whole idea of a conservative force and path independence, okay? We're out of time, so what else do I want to say about this? Okay, this is your let's start again. It's hard to write down here. Okay, that's infinity. It's badly written. So if you start at a really big distance, which is what we started with, that means you're I'm still around with this. As I said, I should have started just with a clean definition. Your book will show you. That's the way the integral looks. This is your potential relative to infinity. And the change in KQ over R, at infinity, KQ over R is essentially zero, right? Is R zero? I've still got it backwards, but there it is. You can read about it. We'll straighten it out next time. Okay, I'm still turned around on this, and I really need to go ahead and just do it the way it should have been done in the first place. Work done by the field on an increment is F delta R equals K Q QT over R squared and delta R. So, and I'll put a summation here. It's this. It's a summation of this. So the limit work as the integral R1 to R2. Doesn't matter in what direction you're going. In this direction, we're really thinking of moving toward the charge Q, the source of the field. But that's not necessary. Work is integral from R1 to R2 then of K QT capital Q over R squared dr. And that's, you better write it out from there's today. Okay, so we get this integral. That's the work done by the field. And that's K times big Q del QT times, it's not over R squared, it's over R, 1 over R1 minus 1 over R2. Looking for space. Okay. Then the change of potential energy will be equal and opposite to this. This is the work done by the conservative force. Conservative force being work done by the charge Q. Well, the work done by the field of the charge Q in this case. Make sure that's right. I mean, I'm going to substitute R2 and give me a negative 1 over R2. Substituting R1 will give me a negative of the negative 1 over R1, which is 1 over R1. And I'm still here. Still appear to be. No, okay. I'm going blind. Looking at this, I think I'm seeing the same things I'm doing here. So that whatever I did to get this turned around is superseded by this definition. So that the no, actually, I'm looking at the change in potential energy. I'm still getting a change in potential energy is the negative of this, which is this. So I'm coming to the same conclusion I came to before. So, as it turns out, again, this is work done by the conservative field. Negative of this is your change in potential energy. Potential energy change is equal and opposite to the work done by conservative force. So all this is correct. The only thing that's incorrect is I said the potential relative to infinity is negative KQ over R. It's positive KQ over R. And I wrote the negative because, of course, that's what you get for gravity, which is an attractive force. So the gravitational force is always going to be toward the gravitational object. And I wrote that down without thinking because I'm not particularly alert today. Okay, so that's the way it is. So this would be correct because relative to infinity, meaning you start from a very large distance, as large as necessary to make your 1 over R1 essentially 0. Then your change of potential, of course, is then 1 over R2. Change of potential energy, it is 1 over R2 times K big Q QT. And the change in potential would be that. And again, if R1 is very large, so that 1 over R1 is negative, you get 1 over R2. So this represents the change in KQ over R. And potential relative to infinity is just KQ over R if you're at distance R. Okay, well, we'll go on with this idea, but this is very important. It's a central concept. It simplifies a lot of things. And I'll just give you a little quick preview. Basically, the electric fields are gradient of the potential. So in this case, the gradient would just be the derivative with respect to R, the derivative with respect to R. It doesn't seem right. Now, we'll work it out.